Even all set?
I'm all set, JJ. Yep.
Okay, all right. Hopefully everyone's had a chance to get up and stretch a little bit and get back at it. I don't think any course on energy would be complete without a good discussion around renewables. And so to lead the way and lead us through this topic, we have Stephen and Michelle.
Great. So yeah, and actually, I thought you were gonna say no topic or no discussion energy would complete without the building envelope. And to me, a lot of times I want to reinforce the fact that we often focus on the active systems, and as Michelle knows, those active systems are the ones that meet the needs or requirements. But the requirements are determined by, amongst other things, the building envelope. So, and if we don't do a job right on the building envelope, as David kind of pointed out, then everything else, follows into that one. It's like that waste efficiency and supply. Katie was talking about, we're more than willing to pay for waste rather than fix it. And she'll be talking more about that on Thursday. But the idea is waste efficiency and supply. And that's where I'm coming in now with the renewables in the supply side of things. So I'm going to do a couple things here too. We are going to have a little bit more time to look at that tool called RedScreen on Thursday, but I'm going to take an opportunity within the context of renewables because, you can do a back of the envelope calculation for a motor or maybe a pump. I don't know if you're good at it, but to do a back of the envelope calculator for a solar energy system, a solar PV, like a solar air heater or a ground source heat pump, that's not easy to do. So I'm going to just give you a glimpse of how RedScreen actually allows you to analyze these systems. Even if you're not going to be user of a RedScreen, I want you to think about this. Say you were thinking about putting these on your facility, or you're incorporating those into a design. I would encourage you to think about asking people to present their proposals backed up by analysis in a fairly standard way. And one way they could do that would be with RedScreen, because it at least allows you to look at, if you've got 2 or 3 proposals, you can compare apples to apples, as opposed to somebody, proposing in this spreadsheet, somebody in that one, and it's hard to know whether they're proposing on the same thing. So don't just look upon RedScreen as something you could use. Look upon it as something you could ask others to use to present their proposals to you as well. So right at the outset here, sort of a bit of context. Why consider renewables? Well, certainly they're going to help us to get that carbon piece down. The resiliency it's definitely part of resiliency, and obviously environmental stewardship for all organizations, including healthcare organizations today, is very important. As time moves on, the business case for these types of technologies is improving. But I'm going to actually show you a way, even if you can't make the case for a PV system fly, I'm going to show you a way, or another type of system, to actually make it work, even by combining maybe some of the conventional things. So building a case out of more than one technology, but including renewables in it. So, there's lots of things to consider. I think the first thing I would say is that we always want to make sure that we're not putting a renewable energy system in to overcome waste and inefficient uses in the building. So going back to what I talked about in fundamentals a couple of weeks ago, we want to make sure we address what we're actually meeting the need of, or what is the need that we're meeting. So are we meeting a need that's too high with the renewables? And certainly this is the path, I think, to net zero as well. If you think about it, at the end of the day, the last step should be putting the renewables on. The first thing is to minimize the usage of the requirement. Next step is to improve the efficiency of the system, and then look at the supply side options. And that could include heat recovery. We heard a little bit about heat recovery today in terms of boilers, but certainly heat recovery steps in there, I think fits in there between improving the efficiency of a system and then doing the renewables piece. So for example, in this little picture I have here, we might track the use of gas to heat hot water into the building. So the first step is always, are we using the water at the right temperature, the right volume, keeping sure end-use devices are minimizing that. And then we improve the efficiency of the equipment, and that's a combustion analyzer. So make sure that we're getting the highest efficiency of conversion of the gas to hot water, right? And then the next step beyond that, and that might imply replacing a water heater, a water tank, or how we're doing it in the system. Then it could be go to renewables, but maybe in between there, we want to recover some of that heat, because we might find that the business case for recovering heat is a little bit better than renewables. And maybe we want to wrap all these things together. In a tool like RedScreen, you can do that. So I really think that when we look at renewables, we don't look at them in isolation. We look at them as part of an integrated solution that starts at the use, looks at the efficiency of the systems, looks at things like heat recovery, and then basically comes in with the renewables at the end to take care of what other things can't take care of. Much more integrated solution. So we've got a number of different renewable technologies I'm going to touch on today. Solar air heating, solar water heating, solar PV, and geothermal. I've got some examples from hospitals or healthcare, and I'll also show you then how we analyze these things in the tool called RedScreen. So in solar water heating, we've got a number of places we can use the heat that we generate from these things. We can use it for hot water, could be used for process. Some solar water heaters. Here's an example. I'm just going to go in my office and pick up this is actually an evacuated tube solar collector. This actually is a flat plate inside a vacuum tube with a heat pipe basically inside it, which transfers heat up to this device up here, which is that this would be a copper pipe carrying your heated liquid, and then that's how you thermally couple it to the solar tube. And you put these in arrays. You might have seen them on houses. These things can create a fairly high temperature water. So, you know, if you're in a fish hatchery, you could use an unglazed collector. But if you're in a hospital and you have a requirement for a higher temperature, a higher quality of heat, maybe then you would look to something like that. So making sure that we use the right tool for the job. Space heating, yeah, it's possible. Swimming pools and therapy pools, that's a good opportunity. And part of doing this effectively is then having places to put these collectors on the exterior surface of the building, right? And the color, the wall surface. So we'll talk a little bit later on about air heaters, but in air heaters, the color is important as well. So I have an example here of this is a Summerland Memorial Health Center out in BC, and where they basically used solar hot water to provide for domestic hot water and in the laundry. It was a good load. In some cases, you can use it for lower grade heat, right? So if you've got, say, slab heating that requires a relatively low grade heat in order to keep maybe a loading ramp or an area clean of snow or ice in the winter. Certainly in some of the European cities, they have sort of these what they call trigen or combined heat and power systems, where they take the heat at a high temperature to begin with, and they cascade it all the way down and use the lowest grade heat for the lowest grade purpose, which might be heating a slab or a sidewalk outside.
Stephen, and if you have solar domestic hot water, you probably should have gray water heat recovery associated with that.
So I didn't hear you that, Michelle?
It should probably have gray water heat recovery if you've got solar domestic hot water, like you said.
That's right. So, exactly. If we're throwing a lot of heat down the drain, before we try to make up for that with a solar system, why don't we look at gray water heat recovery, recovering the heat from that gray water that is going to drain. So here's an example of a solar domestic hot water system. This was actually the hospital, 112-bed hospital, 36 collector panels, the pump per collector storage tank. That system saved 48 tons of CO2, and 40% of the energy was actually provided for by the solar system. I'm going to, I believe, do I have that one here? No, I don't have that one that I can show you. And in that case, it eliminated about 40% in that system, 40% of the carbon. So that 48 tons represented about 40% of the carbon that was presently used by the system to provide that hot water. But to your point there, Michelle, I mean, certainly within RedScreen, we could, like if we look at the screen here, when RedScreen, the way we model this is we model the essentially the hot water load itself to begin with. And then we take the residual load after any measures, which could include heat recovery. So RedScreen actually is built to be able to do this. So and then we model the solar side of it, which is the screen on the right. So again, sometimes having the right tools that make it convenient to do the right things makes it easier to look at these types of designs. Solar air heating, right? Used for solar or heating of interior space, supplements existing heating systems. And there's actually two kinds of solar air heaters. One is the recirculating collector, but the one that's actually more popular is one where you're drawing outside air in through the solar wall, which is a wall I'll show you in a picture in a second, and that can be used to supplement the heat that's going into the building. So here's an example of a solar air heater. In fact, this is on Flin Flon hospital, I believe, in Manitoba. So that black cladding on the outside of the building is a very special kind of cladding. I mean, it turns out that the hospital had a requirement for replacing the cladding in the building. So if you look at the picture on the left here at the bottom, that exterior cladding, or I think it would probably be brick, it looks like it. Anyway, it was not in good shape. And so in order to fix that problem, but at the same time as then take advantage of a solar gain on the hospital, they were replaced, or they cladded it with a solar wall. The solar wall material you can see in the center here, it has very small holes in it, which air can actually pass through, but because of the surface tension of water, it won't pass through it. And so as you see in the diagram here, that air comes in and it preheats the air being used to make up for exhaust somewhere else in the building. And hospitals do have a high requirement for exhaust and makeup, and consequently this would apply quite nicely. It turns out that the further north you are in this country, the longer the sun spends at a fairly low angle in the sky, which is normal or almost perpendicular to your wall. So solar air heaters actually work very well in high latitudes for this reason. So there's a good example. Now, how do you figure out whether this makes sense in your building? How do you figure out that it's going to have an IRR of 17.5%? Well, so I'm going to give you a little bit of a view of RETScreen, and we're going to have Kevin Burke from RETScreen come in and talk to us on Thursday about all the things that we can do with RETScreen. Many of you have probably used RETScreen. I'm just going to look at the chat here. Do we have any? Okay, that's fine. Michelle's commenting that he needs a new mic. Or do I need a new mic? I think my mic's okay, right? So, all right. So you can see on the screen here, this is a view of RETScreen. RETScreen is a pretty complicated tool. I'm not going to give you the ability to use it after today. But one of the things that we will do, JJ, we need to do this, is we need to make sure everybody that's online that doesn't have a training license for RETScreen, we can provide, RETScreen will provide us with a 90-day training license. So a free license to RETScreen for 90 days for everybody that's online. I'll talk to Kevin before Thursday, and maybe we'll set that up. But basically, then you'll be able to try. Go ahead.
No, I was going to say we'll make sure we talk to Kevin and remind him of that on Thursday.
And what I'll do is I've got 4 systems here that I've modeled for this presentation. So I'll actually also provide the files for those 4 systems: photovoltaic, solar hot water, solar air, and a ground source heat pump. So these are real systems that are modeled. And so when I go into RETScreen, what I can actually do in modeling a system, I can first of all tell it about the amount of air that's moving through the system. So I've got a design airflow rate. I can tell it the schedule and the temperatures of that air, but I can also then tell RETScreen about the wall that I have there, and then that I'm going to add this solar wall to. I can describe to RETScreen the solar wall that I'm putting in, and RETScreen even deals with the various different colors. So don't think you'll need a black wall, right? And the characteristics of the wall will change from a thermal standpoint, but RETScreen has those things built in. So RETScreen has a pretty neat little product database too. We can go to its product database and pull up various different kinds of products for this purpose. And there are more than one, even though one of the better ones, I'm going to say, is a Canadian manufacturer of solar wall. That's who invented it, Conserval Engineering. But those resources there in RETScreen, so you don't have to guess about the characteristics of this stuff, and you don't have to necessarily rely upon the suppliers. You have an objective source of information here. So what RETScreen allows you to do then is to calculate the energy displaced from your traditional heating system, which in this case is a boiler, and then to build the business case towards doing this. So we actually calculate the fuel cost savings. We have to put in the cost of the system, and then what it does is generates for us a financial result. And here we have 6.4 years as the simple payback. But I could go even further because, to the point that David made earlier, we have to convince other people about over the life cycle of these systems why it's good to do it. Well, that's where good financial analysis comes in. And so what we can in fact do is we can look at a 25-year life, and we can look at inflation. And maybe if we think that the inflation is going to increase, maybe the inflation on thermal fuels is going to increase by 5% over the next 25 years. Well, that's going to make our investment even better. So we can build a very compelling business case. We have to be honest about what these values are, but again, factoring in inflation, as much as we don't like the fact that the price of energies will inflate in the future, I'm pretty sure they will, that's going to make our business cases stronger. And we can go so far as to do a much more detailed analysis as well, where we consider discounting. So if in a hospital you might have a discount rate or the weighted cost of capital for projects of 3%, we can then calculate things like the benefit to cost ratio. Over 25-year life of this system, the benefit to cost ratio is 8.4. What that means is you're going to get 8 times as much money back as you put into it. So even though this thing required an investment of around $90,000, if we take a look at on the financial analysis, the net present value, it turns out that it's somewhere on the order of $200,000. So there's a very strong tool for being able to make a strong argument here. So not just about, Red Screen doesn't just do the technical stuff. Red Screen does a great job on the technical stuff, but it allows you then to take, your technical idea, even if it's a simple one, and roll through to a business case very quickly. So that was a solar wall, right? Very, it's one module in Red Screen. I'm going to show you a few more. There's other modules in here. So the solar wall is one of them. Has anybody seen a beer can solar collector? That's kind of it's actually a real thing. You take things like beer cans or pop cans or whatever you want to use, aluminum can, and you basically cut the ends off and you string them all together and you put them into a box, and then you basically bring air into them and then recirculate that back to the building, and you paint them black, and you got a nice little absorber. That's a recirculated air collector. If you want a do-it-yourself project for a solar air heater, just Google. I know you don't have to drink beer, you can do it with pop cans, but beer can solar collector, and you'll find some neat little designs out there. So anybody ever built one? JJ, have you built one of those?
No, I haven't. But that sounds interesting, and there's going to be a lot of fun in drinking the beer to build it.
Well, I was going to say, yeah, preparing the materials for that one is certainly a different perspective. All right, so that was a solar air heater, right? So let's move on to a solar photovoltaic. We all know about these systems, and it was interesting that David said as they build roofs these days, or design roofs, they're certainly accommodating the fact that those roofs are going to have to take potentially a solar panel or a solar photovoltaic in the future. What's interesting is that a lot of people think it's about the weight of them, but it's actually about the wind uplift, right? In many cases, right? So that's one. So it's that you do have to design the structure to withstand the loads that this system will put upon it potentially after the fact. So there's other uses for solar photovoltaics. I actually had a very kind of a humorous use. It was actually this shelter outside a long-term care home on my first slides, where you didn't want to run power over to that little shelter, but you could put a solar panel on the roof and a battery and some controls on it. And so they're great for use even on a property where you don't want to have to run a wire, right? Use in parking lots, charging stations, things like that. So it's not just sticking them on a building and offset the consumed energy in the building. But certainly within a building, one can do that. One can embed a system into a building and absorb some of the load that would otherwise be placed upon the utility. And ultimately, if you want to be net zero, that's what you may have to do in that kind of pursuit. Now, the picture I have here is actually a healthcare facility at West Coast General Hospital out west, where there was a fairly good size array of panels placed on that facility. In fact, I've done an aerial, I think that's an aerial view. That might have been Google Earth. I pulled that off. So it's basically another view of the hospital. 407 305 watt modules, 100 kilowatt inverter. And so basically the cost of their system was $258 a watt, right? Or about $2,500 a kilowatt. And I would say the prices are sitting there. They may be a little bit lower today, and I actually just contrasted between two provinces, what that would mean in terms of tons of CO2 displaced. Because if you're in BC, where there's relatively low carbon in the grid for electricity, you'd be displacing about 10 tons of CO2. If you're in Alberta or other provinces where the amount of carbon in the electricity grid is quite high, you'd be displacing a lot more carbon. So even though that internal rate of return may not be super attractive, 10% is not bad. It's better than my RSPs are turning right now. If one of your goals is carbon and you're in the right situation, this could be a real winner from that point of view. Just have a quick peek at how you would do that in Red Screen. I need to go to the right one here. Here we go. I think this is my PV. No, oh, sorry, I didn't pull the PV one up. Okay, let me see here. Oh, I did. There we go. Photovoltaic system. All right, even though it has the wrong picture on it. So what I did here was kind of interesting. I looked at basically the way I use red screen is rather than modeling the whole building with all its usage, I actually modeled the building basically as a certain kilowatt load, 250 kilowatts, operating 730 hours of all the hours in the month at a 70% load factor, which basically says this building with a 250 kilowatt demand would use 1.5 million kilowatt hours a year. Okay, which, you know, if it's a small building, not a large hospital like some of you are. Now, in red screen, we always work with what we call a base case and a proposed case. So the base case is the way it is now. The proposed case is the way we want it to be, which is going to be the improved case. And the difference between those become the savings. Now, right now, I don't have any savings between the base case and the proposed case. So what this is saying is I'm going to put the photovoltaic power system on, which I specified over here, right? So, and I've specified the system that's actually on that slide I showed you earlier, 407 305 watt panels. Basically, we're looking here then at 124 kilowatts. We have a 100 kilowatt inverter, which, given the circumstances, would work in that situation. And that would generate 156,000 kilowatt hours of electricity, right? So I'm going to show you a little trick with red screen. So I'm going to go over to the screen where I get to do the economics. Now this says 13.6 years is a simple payback. Well, that might be a little tough one to sell. Now, if we take it out to a financial analysis, we might actually be able to show that this actually shows an internal rate of return of 10%. So on a long lifetime of 25 years, this isn't too bad, right? I mean, that's better than my RSPs are turning right now. But there's a little trick I'm going to show you here, because we're assuming that we haven't touched the electricity usage in the hospital at all, right? So, or in the facility that we're looking at, or clinic, or whatever it is. So I'm going to go back in here, and what I'm going to say is, let's say that I can knock off, say, 30 kilowatts off their electricity demand, right? And let's say I can drop their load factor to 65%. So that's going to reduce their demand and their consumption, right, by 14%. Okay.
So that's a recommissioning.
Well, that's a recommissioning. So what you're saying is you could recommission this hospital, and how much would that cost? What would be the cost against that? Maybe a few $1,000s, right? $5,000. What do you think, Michelle?
Yeah. Go 20 cents per square foot, let's say.
I don't know the square footage in this hospital, so
okay.
Yeah, so I'm gonna say maybe we'll do it for $10,000, right?
Yeah. Okay.
Right? Okay, and everybody heard Michelle commit to recommissioning this hospital for $10,000, right? Sorry. Okay.
Yeah, no, that was you. That was you. It's all on you.
Okay, so now I'm going to go back to my summary screen here where I get to see the results. And look what happened here. That $10,000, like by itself, you might go, I'm going to cherry pick that project. And maybe my 10,000 is too low, right? Maybe we need to be a little fairer to Michelle today, and we'll put that up to 25,000, right? So that's probably a pretty generous number there now. I go back. So now I got a project that has, if I'm recommissioning the hospital, 0.7-year payback. But now let's say I want to do my photovoltaics. So when I turn on my photovoltaic project, which is 13 years, now I've got a simple payback of the two of these combined. Now, some people can always come along and cherry pick that recommissioning. But if there's a commitment to reduce carbon at the same time as we're doing this, and we want to do the photovoltaics for other reasons in addition to the carbon piece, then here's a way to combine the economics of these two things and make a much more compelling financial case overall. So now when we go to look at the internal rate of return based on an inflation rate of 4%, 25-year project life, now it's 20%. So by doing that, we've doubled the internal rate of return, and we can actually even roll on to a more detailed financial analysis. I'm going to set the discount rate here to 3%, and I'm not going to borrow any money to do it. So now I'm looking at a benefit to cost ratio of 3.6, which means this project is actually going to return to me 3.5 times as much money as I put into it. Even though it's a significant investment, I'm getting a multiplier coming back because this is a good investment. So part of getting these projects done, I think, really has to come down to looking at things over the long term. Question or comment?
And what you just did is actually very common in EPC. When there's an energy performance contract, they will often bundle projects like that, like some recommissioning with their high cost project, because they want the long-term savings, they want the greenhouse reduction. So they do bundle exactly as you did.
So, but you don't have to do an EPC to do that. You could bundle these things
No,
together.
no, you don't.
Yeah.
It was just an example. That's something they do currently in EPC.
So it's a technique, but anybody can do that. So there's just a thought, right? Like looking at building sort of more holistic approaches to this. And the argument can be, does it make sense to spend the money in PV without spending the money on this? And does it make sense to miss the opportunity to do the photovoltaics, right? So you can make a strong argument both ways on that one. So that's red screen for another purpose. All right, let's have a look what else we have here. Oh, this is one of my interesting ones. Geothermal systems, right? So here what we're doing is we're using heat from the ground, obviously, to introduce it into the building in some form or fashion and offset the purchase of standard systems, a heat pump system, basically, right? Not saying we're building a building beside like you know, a big like the heat geysers or whatever. No, this is just really just taking heat from the ground at a relatively low temperature and raising the quality of that heat up to a higher temperature so we can use it in the facility and provide cooling at the same time. But we can maintain a relatively high, we call refrigeration coefficient of performance, maybe 4 or above. So that means for every unit of electricity we purchase, we can deliver 4 units of heat from one of these heat pumping systems. That's, you know, again, that's pretty good because that takes the cost of electricity now and all the other things attached to electricity like carbon and cuts it by a factor of 4, right? So that's the benefit. But I was looking at electrical or mechanical business news a little while ago, and this is the Quebec City Hospital, and they were talking about the engineering of the geothermal system. And basically what they said here was a lot of engineering was put into maximizing heat recovery before we sized the geothermal system, said the engineer. It's much cheaper to recover internal heat versus digging around in the ground to reach the heat in the soil. So we took as much advantage as possible existing energy in the building. And I would argue that you do your efficiency first, then your heat recovery as you're talking about, and then, so that way you're building an integrated system, not that's using heat from the sun in this case, but it's using heat that's already being generated in the building as a byproduct of things that are happening. So holistic approach, right?
Yeah, and on Thursday, somebody from that project, maybe not from that project, but from the company that was involved is going to be there on Thursday.
Oh, nice. So I'm just going to quickly finish off, just showing you how red screen actually can analyze a combined heat and power system. And that's really what a heat pumping system is. It's under the combined heat and power model. And in fact, red screen has then the ability to model these types of systems where you're sourcing heat from the ground and you can put heat into the ground as part of cooling and maintain a fairly high efficiency of doing both. So this is what we call our system selection. Red screen allows us to tell it the relative prices of the natural gas, the source of heat in this case, and the electricity. We can specify the heating load, right? And I've just specified a very simple building, single building space heating requirement, but we can have single or multiple zones in a building where we build this one out in a lot more complicated, as many zones as we want. I'm just using a very simple one here. And I give the heating load in watts per square meter and a domestic hot water load. Right now, what's interesting is I even have the ability in here to say, okay, before I actually get into using this heat load, that is the heating load here of 60 kilowatts and a consumption of 20,000 cubic meters of gas to meet that heating load, I can put in conventional measures at a cost. So again, that philosophy is carried through. Even before we do the heat pumping, maybe we want to take advantage of what we have in the building already. In that article that I read, it talked about doing it with heat recovery. I would even think about conventional measures, which could include heat recovery and just other things that improve the efficiency of the building, like fixing the windows, the infiltration, all that kind of stuff. So there's lots of ways, and Red Screen has some amazing building envelope models if you want to model the stuff that David talked about earlier. I'll give you a glimpse of that one before we, no, I won't do that today. I'll leave that for Kevin on Thursday to tell you about all the things that Red Screen can do. So I can model the cooling load in the building. Again, how many watts per square meter? I can put any conventional requirements. I assign the cooling load to electricity, and I can specify the COP of the conventional cooling system. And I missed that one here, but I can also specify the efficiency of the conventional heating system in this case. So I've kind of specified the heating and cooling system. And then I can tell something about the load. I can show the heating and cooling load, right, on a monthly basis. So these are my load curves, my heating load, my cooling load. and I have the proposed heating and cooling load. So if I were to go in and say I could reduce the cooling load by 50%, say by window films, right? Then over here, it ripples that through into my proposed case. So I can manipulate those loads before I apply those loads to the heat pump, the ground source heat pump system. I'll just leave this one back where I had it without that reduction in load. But you have the ability then to, again, look at an integrated solution in these situations. So there's your monthly heating and cooling load. And then you can specify the cooling equipment, right, which in this case will be the heat pump and its capacity. And we specify its capacity, but also its performance. So here we say it's got an efficiency of 400%, which is basically BTUs per kilowatt of 1.3. In fact, this one should be 4, not at 400%. There we go. And the BTUs per kilowatt are 13.6, or the SEER value of that system. So a little bit of a typo there. And then we have the heating system down here. Its conventional efficiency was 70%, but now we're going to a seasonal efficiency of 400%. In this case, a 400% makes sense. That's the same thing as a COP of 4 on the heat pump side of it. And when we're done, then we see the way that system performs, the energy delivered against its capacity, and we then see how we can operate that system. And eventually all of that gets flowed through into our financial analysis, where again, we can do a long-term analysis. Now, in this case, it probably doesn't make sense. And this is why the engineers over in this situation said, okay, it makes more sense to pull heat from the building than pull it out of the ground. So what they did was they supplemented that project with conventional heat recovery and other things within the building. So here we're looking at a 4% internal rate of return in this situation, and probably not an attractive project to go ahead with. But again, using RETScreen, we can look at this stuff relatively quickly and understand what is the best way to operate the system. So that's a very quick tour of RETScreen. Again, I'm going to leave the big picture on RETScreen. Now you've seen how we apply it to some renewables to Kevin during the session, Kevin Burke from RETScreen on Thursday. So I think that's all I was going to cover today. I didn't want to drag things out as we're getting close to the end here. So I will open the floor to any discussion. And we see we've got a few things going on here. So, okay, JJ, maybe you can narrate the things in the chat, because I haven't been keeping up with them.
Well, we've had some chat back and forth about the obvious benefits of RETScreen. I mentioned to everyone that, you know, there's many benefits. One of which is that it actually compiles and writes the business case report for you, which is wonderful. As a touch of a button, you can have a 10, 11, 12-page business case right there to present to your VP of Finance and get funds for projects.
I'll do it right now.
Yeah, and Rob confirms that he has done that exactly, done that exact thing with feasibility studies to put forward, you know, a case study for money to get funding for projects.
So on that project I just did, I just clicked the button, create report, and then I'm exporting the report to a PDF. And then, as you said, it's, I don't know, it's probably a 20-page report from one end to the other with all the details in it. So, and I'll just pull up the PDF file right now. So hang on. No, I tried to open it with RETScreen. You can't open a PDF file with RETScreen. There we go. So there's our report in all its glory. I can show you on the slide sorter. So you created that report with a few clicks after you created the project you have. And sometimes the projects don't have to be complicated. That was probably a more complicated one. That's the solar wall. But RETScreen is useful for simple and complicated projects, one and the same.
And that's exactly how fast it happens. And it even gives you an executive summary if you click on the requirement for that. So.
Yeah, we've got your executive summary, which shows that financial case. There we go.
Perfect. So
All
does
right.
anybody have any questions for Stephen or Michelle?
I can just go back to the ground source. I've been approached many times, not as much in the healthcare as by municipalities that want net zero emission. Because you have to be careful, net zero energy, net zero emission, they want a zero emission building. And I tell them right off the bat, no natural gas. You gotta have to go some sort of heat pump, because if you want no emission, you want very likely to go to heat pumps, and actually that actually ties into what ThreatScreen can give you in terms of what kind of savings you can get out of that.
Yeah, so I was analyzing the system, the heat pump system, the ground source heat pump. I had my heating and my cooling load in there, and I had the load characteristics, right? This on an annual basis. But then ThreatScreen also has an emission tab here, right? Click on that, and then it basically looks at the benefit from the point of view of the carbon side of it. And if I were to place this system in Alberta, let's say, not to pick on Alberta, but it is one of the highest carbon ones, right? So in that case, you're not going to see as much benefit. Why? Because you're using electricity that has a high carbon content. But if we were to move that system over to look at that, that's in Quebec. In Quebec, we go from this to this. So we have to be careful where we place these systems, and you're 100% correct, Michelle. You got to get rid of the gas. But if you're replacing with something that has more or less carbon in it, the benefit is going to be different in those situations. So I'm not saying it'll work everywhere, but the beauty about a tool like this is you can very quickly test its sensitivity to the circumstances that you're in, and then you don't head down the wrong path.
So we do have a question coming up from Julia.
Yep.
She's just going to open her.
Oh, yes, sorry. Hi, everyone. I have a question actually for Michelle. I think during the pump session that at the end of Stephen's pumping section, you made a comment about there's a rule of thumb for the cooling tower savings. You said if you can, I forgot exactly what you said. I think it's zero for every 1 kilowatt or one, I don't know, reduce, and you can save 0.3 kilowatt or something. This is for the chilled water pumps, because you're trying to help us prioritize what to.
Yeah, that's for the chilled water pump. That's the interactive effect. So for the chilled water pump, for every kilowatt hour of pump saving you do, you can add between 0.25 to 0.33 additional kilowatt hour of savings from the chiller. So that's on the chilled water.
Okay, so what does that mean? So for every kilowatt hour of pump savings, you can save 0.33 kilowatt hour of what?
Of chiller energy, so of additional electrical savings. So,
because any heat that you remove, right, from the water that's being cooled by not moving that water, right, by not circulating an impeller in a pump unnecessarily, any heat you remove then doesn't have to be removed by the chiller system. So you use the COP of the chiller to figure out how much you're going to offload the chiller or the input of the chiller by taking that heat out. It's just the same as removing a cooling load anywhere in the building. It'll be the same thing.
So that's with VFDs, or I forgot what the context was. Like, or is this like a?
Well, I think Michelle was saying using VFDs on a cooling tower would be one of the first things he would look at, correct, Michelle? Oh, we might have lost Michelle. But
I had a hard time on, yes, absolutely. Cooling tower, I would actually put VFD on the cooling tower, but I would look at the pumps on the cooling tower. They're usually oversized, and either they are throttled or they have too much flow. So yeah, both, like Stephen said, fans on the cooling tower, VFD on the pumps of the cooling tower if they are either oversized or throttled, and then VFDs on the chilled water pump, even if it's not a variable speed, just to turn down the flow if it's over pumping or if it's throttled.
Because over pumping simply creates heat that has to be removed by your chiller anyway.
Oh, is that where the savings from the chill water is from?
That's the knock-on savings, yeah.
Oh, okay. Thank you, Stephen. Thank you, Michelle.
We have a comment in the chat too from Christian Tam. He agrees with Michelle that Middlesex Center did just what Michelle was saying. They got rid of gas and used geothermal in their net zero fire hall. And for those who, you know, sometimes when you travel Ontario to different facilities, you get into the north and people there say, well, geothermal won't work for us. But I can tell you that in Moosonee, there's a medical center that uses geothermal, and they do very well on that system. And Katie Cowan, who's online with us today, has actually been to that facility and seen the system at work.
Yeah, I think it's an important distinction to make there about how you actually get to net zero or carbon zero. And you know, and again, because we've got people from right across the country where you've got different fuels like gas, oil, and so on, and in the north oil, and then you've got different content of carbon in the grid. There's no one answer to the question what works, and that's where doing a, you know, even a very basic simulation or model in RETScreen just at the beginning of a project, just to see if it, you know, even begins to make sense, is so important. Otherwise, you can spend a lot of time pursuing something that may not work, or maybe you'll miss something that will work if you don't do that. So, right.
Okay, seeing no further questions or hearing no further questions, I guess we'll call an end to the day. And thanks everybody for joining us once again. Thursday we start again at 10:30, so if everybody can be logged on by say 10:15, just so that you know, we have a good count of people before we get started for the day. And thanks once again, Stephen and Michelle. Good presentation.
Thank you, JJ.
Thanks, everybody. I'll put my sunset picture up there.
Yeah, always a good one.
Thank you, guys.
Thank you, guys.
Thank you.
Mm-hmm.
Hi, Con, did you have a question?
No, I'm just logging off. Thank you.
What's that? I didn't hear you.
I'm saying I'm just logging off. Thank you.
Oh, you're welcome. Your mic's breaking up a little bit there. I can't always hear you.
Steven?
Yes, Julia.
Hey, sorry. Hi. If no one has a question, can I ask a quick question?
Sure. I'm gonna hang around until everybody logs off. So if you're still here, then yeah.
Okay, cool. Hi. I'm a little confused about the answer earlier about that chiller water thing, right? So the context is to introduce VFDs into your cooling water pump.
Well, he
And
actually
then-
talked about 3 places to put the VFDs.
Right,
Um,
right.
So one of them is on the chill water pumps within the building, right?
Okay.
So
Yeah.
that's I'm just gonna let my dog into my office here.
Okay. Yeah. Thank you.
That's the one that circulates the chill water throughout the building. So any additional heat in that loop will become cooling load on the chiller. All right. So
Okay.
the next place you could put a VFD would be on the cooling tower pumps, which move basically the water from the chiller up to the cooling tower and back, right? So they circulate
Right.
between the chiller and the cooling tower to cool the chiller. And then the third place would be on the fans on the cooling tower. All right.
Fans on the cooling tower. Okay.
Yeah. So you can modulate the fans on the cooling tower because you may not always need them at full speed depending on the conditions. Okay.
Right.
And again,
Okay.
if you've got a varying cooling load, you may be able to modulate then the speed of so your fans and your pump will kind of go together, right? Because if you need more cooling, you need more fans, and so you run those. but that's on the rejection side of the chiller, right? So anything you do there you'll save, but there won't be an additional saving. But anything you do on the load side of the chiller, that is, if you slow the chill water pumps down, the pumps that circulate the chill water within the building, that will actually take heat out of that water, right? Because you're no longer stirring it up and creating more heat.
Okay.
That will result in an additional saving beyond just running a variable speed drive slower and saving electricity to pump. The heat that you're not putting in the water now doesn't have to be removed by the chiller. So typically, if you have a chiller COP of 4, right, or say 5, if you have a chiller COP of 5, if you remove 1 unit of energy, right, by say you remove 5 kilowatt hours from the water by not over circulating, you'll save an additional kilowatt hour at the chiller because you don't have to remove that heat by the chiller anymore.
Oh, it's 1-to-1 ratio.
No, it's a 5 to it's whatever the COP of the chiller is, right?
Right.
So if it's 5 kilowatt hours you remove, and you have a COP of 5, then you remove, then that's 1 kilowatt hour the chiller doesn't have to use to move that heat.
Right. Okay. Interesting. Okay. Yeah. No. I'm interested to learn more because we have this building that has it's all water loop for heating and cooling. So I'm trying to understand where there will be some energy efficiency opportunities.
So that's one loop, and you've got basically heat pumps in each zone.
Heat pumps.
You said you have one loop for heating and cooling.
Right.
Is that what you said?
Yeah. So the water. We have water only for heating and cooling.
Yeah. So, but is there one loop for heating and cooling, or is it like, do you have heat pumps in each zone, that water to air heat pumps for heating and cooling of the zones, or
no heat pumps.
You have a separate loop for heating and cooling then?
Oh, is that
like
right?
I'm asking you, what's the configuration? Is like 2-pipe, 3-pipe, 4-pipe system?
I have to find out because yesterday I was only looking at the BS system and then I was actually very confused. It's
always easier to have a picture of the general configuration of the system when you start to ask those like when you're looking at it and sort of saying, what can we do here? It's
right.
sort of see if you can draw out the overall system. Sometimes that's not always obvious, right? And you have to, and the detailed drawings don't help because they're fairly complex. What you need is a fairly simple schematic view of the system, and then you can kind of talk about how it's operating.
Okay, I see. And I think the answer is I have a separate heating and cooling loops. Yeah, sorry about that. We do have separate. Yeah, cool. Okay, thanks so much, Stephen.
You're welcome. Happy to answer questions afterwards.
Okay, will do. I have lots of questions always. Thank you, Stephen. Have
You're
a good
welcome.
day. Okay, bye for now.
Bye now. Does anybody else have any questions? If not, I'm going to go ahead, and if anybody wants to continue copying things from the chat, but otherwise I'm going to shut the system down in about maybe a minute.